Okay, thank you very much, Chairman, for this nice invitation. Really, it's a pleasure and honor for me to be here. Although I feel a bit like an alien because I come from the computer science background, but I try my best actually to be aligned, with the scope of this conference. So this talk about AI and how AI can help innovating, okay, and giving new solutions in digital pathology. Let me first start by this statement, okay, to make things clear and to have our feet on the ground. I would say that a machine or a system, whatever it looks intelligent and smart, but at the bottom line, internally, what it does, it deals only with numbers. And it does only for operation, for arithmetic operations, addition, multiplication, division, and subtraction, nothing more. So we have to keep this actually in mind because it's very important, and maybe to understand really the difficulty, but we want to apply AI and machine vision in any given applications. Now for artificial intelligence, there are many definitions, but the one I prefer is this one. It's the study of models, computational models, that aim to keep the machines with some capacities that she can perceive data, reason and think about this data, and then act on this data, okay? And this is what we do as a human. As a human, we perceive information through our 5 senses. We treat these informations, and then we act based actually on that. So I believe it mimics very well, the human approach about, intelligence. Now, when the data is visual, and it comes through images or video, here we talk about computer vision. So computer vision, it can be looked at as a branch of artificial intelligence when the machine, okay, tries to understand, analyze the image or the video to come out with the given decision or given understanding. So the ultimate goal is to turn the pixels which are in the video or the image into kind of structure, into kind of understanding that will allow to a given decision, making. Now, let's go to our application. It's digital pathology. Maybe you or some of the audience are more familiar about that. So as you know, pathologists, when they want to analyze something in the patient, so they take a biopsy, put this under a microscope, okay, they get different magnification, and then they look to the cells, right, to the landscape, all right, and then they come out with a given, analysis or given diagnosis, all right. Our applications is the automated classification of the cells within that particular kind of image, the whole slide images. So we try to segregate this, population actually of cells in different classes, depending actually on the context. For example, epithelial, fibroblast, etc., neutrophil, all right? And this, it can have many applications for the cancer research. It allows the physicians or the pathologist to examine at the micro scale, the tumor environment. In the drug development, it allows also to assess the response of the tissue to a given drug. And the precision medicine, if you want to tailor, a particular, our treatment to a particular, patient. So in this operation, in this classification, operation, when you want to classify the cells and put them into different, groups or clusters, the basic operation, of course, is to compare a pair of cells and tell whether they are the same or not, or whether they belong to the same category of cells actually or not. So if you have 2 cells, type A and type B, we want the machine to tell whether indeed, okay, they are different or they might be the same. So now the questions, how the machine can compare images, all right? Again, we have to go back to what I said at the beginning. The machine deals only with numbers. So an image, if you look into your machine, is nothing than a matrix of numbers, all right? So we need to deal with the numbers. Maybe the first reflex that will come to us, comparison, it can be implemented using subtractions, because to compare, let's say, numbers, what we do, we subtract them. If the result is 0, they are equal, otherwise they are different. So maybe this will be our first attempt. But the issue don't work. Look at this images, it's the same style, but because of the staining process, they look different. So one is dark and one actually is clear. This, of course, going to reflect, on the numbers. If you subtract, you get something different, even though it's the same cell. So there's an issue here, all right? The basic operations which the machine performer won't be able to solve actually our problem. Those solution, we have to go back now to the root, to the origins, and to this guy, which is called David Marr. So David Marr, he is the founder, if you wish, of the computer vision. And even though he died at early age, about 35 years old, his legacy and his vision actually is still shaping the research in computer vision. So in his book, which I got the chance to look to read during my PhD, he was describing, the process actually of visual perception. And by the way, he's neuro scientist, not computer scientist. So he was insisting on the concept of representation. So the vision, in fact, is the mechanism by which we represent shapes, in the image, and put this actually into a kind of functional structure. And he was really insisting on this, okay? So at the end, if you ever given a problem with the visions, all the efforts should be dedicated on how you represent the information. After that, all the rest, okay, going to be set forward. And the decision, it won't take too much time, or it won't be as much as difficult if you can manage to come out with the adequate representations. And to showcase actually his theory, he will give this kind of example, which I love to give to my students in computer vision and AI first. So it's a very simple actually problem. I ask my students to subtract these two numbers. All right. So you can imagine their reaction. They start to laugh. This is not actually a problem. We can use just our calculators. So I give them the same problem, but instead of using the Arabic numbers, I put the numbers into the Roman representations. And here, of course, it becomes difficult. Yes, it's difficult, very difficult. But the difficulty actually is coming not from the operation. It's the same operation, subtraction, but it's coming from the representations. So in my research, actually, I've been very, affected by this kind actually of vision. And all what I will present right now is in this direction, how we can come out with the best representation to solve our problem of tissue, phenotyping. So if you're going to now design actually a model, a machine learning model, to solve this temporal problem, we have here two types of, cells, type B and type A. And we want the system to tell us whether they're the same or not. This is actually our model. But as you can see, 90% of it is about deriving, the best representation. And now I can tell you, for sure, take any model out, the transformers or the LTCM. If you look at them, you see that maybe up to the last stage, up to 25%, it's only about deriving the representation. And the rest part only about the decision, for example, the classification. What we want to achieve at the end? Ideally, okay, we want our systems, our representation, to map these two types of cells into a single number. Let's say in the range 0 and 10. So that the range of each cell here is different. So the two representations here, this representation should give us a kind of separated, range, like the blood test, okay, which is actually ideal. But in reality, this is what we have. The representation is, overlap, disentanglement, all right? And I will say now all the research in AI, in computer vision, in machine learning, is how to disentangle, how to come out with a representation that can separate the different classes, in our problem. And it's still an open problem. This is really what machine learning is about, in my opinion. So our first approach here to, this problem about comparing two cells, this is also based on the feedback from the pathologists. Okay, the cells are communities, and they interact between, each other. So they have to be looked as such. So if you take the human example, if you want to establish a connection between two individuals, all right, if I integrate their relatives or their neighbors, this will help me to confirm or to negate such kind of relationships. So that's actually what we did. We don't consider a cell alone, but we consider its neighborhoods in the form of a graph. So a graph actually is a structure composed of nodes and edges. So the edges represent a connection between two cells in our examples. And then we feed now our models with these two rich representations for the cell itself and that its surroundings, and then we show that this might help, or actually it helps to provide better representations of our cells, and we present this into the image processing, journal about 2 years ago. So this is the full, pipeline. Don't need actually to go too much into details, but this is one the best idea. The second paradigm which we looked at is now what you call the vision language models. Maybe you heard about ChatGPT, etc., the Lava, etc. So a computer or vision language models is an integrations of this advanced, LLM models with the computer vision systems, okay? So the idea comes from the fact that when we learn, some information about object from an image, in the same time, we acquire some textual description about the image. For example, here, an image of an apple, but we can say also that is a red apple with an apple with a smooth surface, okay? So our brain accumulates or gets this two information, and he gets also these relationships, this association between the text representation and between the image representation. And this has been inspired actually from some research in cognitive science. They show that the posterior cortex and the temporal lobes before, they intervene in this kind of multimodal, learning. So we say we can apply this to the, pathology. So we can consider an image of a cell together with its description, which comes actually in the textbook of any kind of medical, report. Moreover, we can put this to the extreme. We can consider the description, but we can consider the cause, of the pathology. We can consider the symptoms, and all of this now going to be integrated, together. We can consider the same thing for other type actually of cells, and then now our learning going to integrate this rich, information, the image of the cells and all the information about its cause, about its symptoms, and we show that this kind of learning helps again, in disentangling the representation of the different type of cells, and this was our publication in the CVPR, this top conference in computer vision. Moreover, this again based on the feedback of the pathologist. When they examine, this whole slide image, they do this at a different level of magnification. The more you zoom in, the more pattern, the more information, and the more descriptions. So again, we can take this up as a whole package, the description at different levels, and feed this to our learning models. And again, we show that this helps to better classify the different type of cells. And this was our recent paper in CVPR, this year. Finally, we go back to the initial representation about the graph, all right? So all the previous methods, what they do, it's one pass, We have actually the image, we pass them actually into the, model, we get our classification. But as you know, what we do as a human, we review our assessments. We go through many iterations, to enhance, and to revise our assessment. We say we can do the same thing. But what's new here, that at the very beginning, we assume that all the cells are connected. So they belong to the same category, if you wish. And then we repeat, browsing the whole graph, the whole landscape, and at each time what you do, we check whether each pair of cells are indeed correct or not. And then we iterate, and we show that this gives very good actual results because this is kind of enhancement, and we produce this into the image processing, journals. So I'd like to thank all my team and my collaborators. It's really, a teamwork, and thank you again for your patience and attention. Thank you.
Thank you.